Can you believe this? Why don't you take a look at this? This is the greatest homework problem ever in any textbook ever written. Look at this one here. Can you see it? It says, convince your dog that a PDA can do anything an FA can do. That's right. Don't explain it. Don't write an essay about it. Convince your dog that a PDA can do anything an FA can do. There you go. What a great book. What a great question. Can you do it? Can you convince your dog of that? Might depend on the intelligence of the dog, but maybe it depends on the intelligence of your explanatory power. Maybe be able to talk about how a PDI can do anything an FA can do. Maybe the reason that they're saying to do it to a dog is that it's one step, or maybe it's pretty simple. So think about it. Think about how to do that. Okay, this is our last video on pushdown automata. And now we're going to go grammar to PDA. So this is the same sort of process that we did with the NFAs and the DFAs. We took languages and grammars and the machines, and we were able to go from any one to any one. So now we're going to repeat the process here. We're going to go from a context-free grammar, CF grammar, context-free grammar, to an empty stack PDA. So here's the idea. This is the grammar over here. And again, remember the difference between context-free and regular grammar. You should be able to identify the differences. So we write down what the terminals are, and then we can come up with the PDA instructions that correspond to these different things over here. So here are the different productions. We want to write them all out in this way. And we just convert them. And then we get the instructions straight from these productions. So let's go through this line by line and see what's going on here. So the first rule is to take the terminals and convert them straight into instructions of this type. You start in state 0, you get an A, there's an A on the stack, pop, you end up in state 0. This is just the instructions for the terminals. Then the productions have this stuff here. This is in the angle brackets. This is a shorthand notation for denoting a sequence of stack instructions. So I start in state 0. I can have whatever comes in, and then S. These are all the start states, see? And then these are whatever the non-terminals are. And then over here, you have inside this bracket, you have the production. So pop, and then push B, push S, push A, B, S, A, because we go from right to left on these things. So you can just spend some time with this and see the pattern match, and then you have it. It's just an algorithm, and it's pretty straightforward. It's so straightforward we can program it. One of the beauties of having an algorithm, we can do the programming, and you can come up with a PDA for any CF grammar. Regular grammar satisfy the conditions of CS grammar, so you can do this for regular expressions as well. And you can go the other way as well. This is a little more complicated because there's multiple options here. So let's look through the different graphical representations, the different instructions we can have, and see what productions we get out of them. So here, if you start in A and go to J, and you're popping with an A on the stack, and you get a B on the stack there. A is the input signal, and B is on the stack. Then you go from B, right? This grammar production, this symbol here is going to be called Bij, goes to A. So this is the opposite, see, of this one here, where we have this construction. We now have this. And if you go I, J to K, then you're going from Bik to A times Bjk, not times, but this is just how the production rule goes for each state K. And I agree with you that these subscripts start to get really complicated, but you have all of this right here. And you can just, I'll ask you to do a problem like this on the assignment, and you can just look at this and just draw the connections. And by doing it, then you'll see it. This isn't really the kind of thing that I can say a sequence of words that puts it inside your head really well. Some things I think can be helped with that, but not really this. You just kind of have to spend some time looking at this. I do have an example here. So here's an empty stack PDA. We'll convert this into a grammar. So state 0 gives S goes to X00 and X01 based on these two transitions using the rule from the previous page. Then the pop operation, so that's going to be this one over here on state 1. So we should be able to translate this instruction, this PDA instruction, from this tuple form into the diagram form. So now we have the 1AX pop 1. This gives us this construction here. Again, this is the repeat from what we saw on this side over here. And then 1A pop 1, this other one. So both of these are the two that you have here. So we have these constructions over here, the X and the A. These stack symbols are going to be the ones that represent the non-terminals. And all this subscript is doing is helping you understand which one goes in which place. So you could end up with multiples that are just determined differently. And then when you finally convert this back into an actual grammar, you could just rename these if you don't like the subscripts. The no-op goes along this way, and then the push gives you this. So really, it's, I'll say that straightforward, but I know that these words that I have strung together have left you with a deep cloud of fog about this. So I guess I'll say that, especially for this particular video, I'm just going to give you an assignment and look at the last portion of section 11.6. Yes, it's 11.6, where they go through examples like this. So you can just see that there. They do an example too of the PDA to the grammar. So just run through that and do the one. The assignment's not going to be onerous. It's just going to be one of these. So just spend some attention to detail and run through it. One of the interesting takeaways here is that non-deterministic PDAs are more powerful than deterministic ones. We did see that with the DFAs and the NFAs. So you might think that's always the case, but it's not. And here's the example here. This is a really interesting example. We have the even palindromes over this binary alphabet. Here's the context-free grammar for it. And it says here that any PDA to accept the language must make a non-deterministic decision to start comparing the second half with the reverse of its first half. Non-deterministic decision. This means that we don't really know where the middle is, because we don't know the length. We don't have that as one of our inputs. So any PDA that's going to try to see is the second half the same as the first. That's a palindrome, right? The second half is the same as the first half. So we want to be able to know that. So basically what we're doing is we're doing two things at the same time. We're reading in every single element of the string, but also every single step, we're launching a separate PDA basically to check to see if that's a palindrome. And this is where the non-determinism is. Every time we go, by the time we get to, so we read in the A, then we read in another symbol, and now we're instantly checking to see, we're both progressing on the sequence here, and we're also doing a check to see if the string is over and see if we're at the halfway mark, because we don't know where we'll be at the halfway mark. So you can picture this as this beautiful multi-bifurcation. It just keeps breaking apart. Every time you go further on this sequence of characters, every single new character you receive, you have to assume that's the middle. You have to assume that's the midpoint, and you have to then start checking to see if it's the same on those. So every single time you accept a new character, you are in a position of generating a new sequence where you're doing the check. So it's kind of like a bunch of recursive functions all going at the same time, all in parallel. It's just deeply, deeply non-deterministic, because non-determinism in this context means that we're in a state machine, that we're in multiple states at the same time. I don't know if this was any more clear or not. I've been talking too long and maybe this isn't clear here, but this is a really important line, and it's worth spending some time on and just thinking about. This grammar into a PDA, the solution's pretty straightforward using the algorithm. Just convert all these different things straightforward into these instructions.